we take another look at the collision of two objects in the center of mass frame, and we'll see in a couple of minutes how we get the center of mass frame if we know the velocities of two objects. But we have this collision in the center of mass frame where the first velocity is 4 meters, with the velocity of the first mass, which is a 100-gram mass, is 4 meters per second times I. Velocity of the other mass, which is a 200-gram mass, is negative 2 meters per second times J. Now this was from a previous class, so we've already worked this one out. In the center of mass frame, if the collision is elastic, meaning if kinetic energy is conserved, the after collision velocities will just be equal and opposite to the before collision velocities. So both objects end up with the same speed, therefore the same kinetic energy. So the kinetic energy of the two object system is the same after as it is before. And the momentum is the same after. Total momentum is the same after as before. Total momentum is 0 before, it's 0 after. Very easily verified. So we understand that conservation of momentum is satisfied, and conservation of kinetic energy in this case is satisfied. That's not the case with most collisions. Conservation of momentum does not imply conservation of kinetic energy. Now, energy conservation does imply that the kinetic energy after can't be less than it is before unless you have some change in the potential energy of the system, like from an explosion or a spring or something. Okay, well, now we want to observe this collision, this time from a frame of reference that's moving with velocity 2J, 2 meters per second times J. Is it 2 meters per second times 3 meters per second times J? So that we have this velocity in the J direction and this is a new frame of reference from which the collision is going to be observed. We could imagine, for example, a drone flying overhead tracking the positions of these objects. The drone has no idea. The drone's not tracking the ground. The drone doesn't know how fast it's moving. But we, measuring it, notice that it's moving at 3 meters per second in the J direction. All the drone observes is where these two objects are within its own frame of reference. So what does the drone see? And what do we see? Okay, well, what we see, this is moving twice as fast as this. When this one's moving to the right, this one's moving to the left. So at some time, this object is here, and this object is here. And the frame of reference of this drone, which is moving, as we know, relative to the ground or to whatever frame we're measuring from, this drone is moving at 3 meters per second, taking its coordinate system along with it. We'll also assume that its x-axis is parallel to our x-axis, and its y-axis parallel to our y-axis. Okay, so at the same time this mass is here and this mass is here, we're going to say this white arrow indicates that at the same time the reference system is here. Our x and y axes of our drone system are here. Now a short time later, the two objects are here and here. This one has moved this far, this one has moved half as far. And the coordinate system has moved. The coordinate system has moved not as far as this one moved, but further than this one moved. I don't know if I got those distances right, but that's the way to understand this diagram. So short time later, here are the two objects, and here is the coordinate system of our drone. Well, in the drone frame, what does that look like? Well, here is the drone frame at the first instant when the masses are here and here. So the masses will be here and here in the same positions in this picture of the frame as they are relative to the frame whose origin is here. This one is up and to the left, this one is up and to the right. Now, during this short time interval, both of the masses have moved and the drone has moved. So that as we would see it, the x-axis of the drone system is closer to the objects than it was before. As the drone would see it, those objects have moved in the x direction closer to the x-axis. Now make sure you can digest that statement. Either way, we see that in the frame of the drone, the drone frame hasn't changed. Okay, so this frame is still the same, but within that frame, these two positions look like this. Why? Because the x-axis has moved this much closer, so those objects will have been seen by the drone frame to have moved that much closer to the x-axis. Now they've also moved in the x direction. Okay, this one twice as far as this one, so that this one has moved over to here, and in the drone frame down to here. This one has moved a shorter distance in this direction and toward the x-axis. The result is going to be that the vector that describes the motion from here to here is going to look like this. Now that's the vector that describes the velocity. The vector that describes the displacement would of course go from the center of this mass to the center of this mass, to the center of the same mass at some time later. But this is going to represent our velocity. It's going to be in the direction of the displacement. And this velocity will be in the direction of the displacement. Now the x displacements are both the same because the x displacements in the drone frame, as we've said, result from the drone frame having moved closer to the position of the object, for the x-axis of the drone frame having moved closer to the objects. The horizontal motion of this object is greater than the horizontal motion of this object, so this vector is going to be steeper than this vector. And then I've got a dotted line from each of the vectors indicating the path that these objects are going to take if they don't collide. Okay, now how can we be sure they collide? Just because they move in the same path doesn't mean they're at the same point at the same time. This one could easily cross the path of this one before this one ever gets there, or vice versa. Well, we know that's not going to happen. And the way we know that's not going to happen is because they're both moving at the same speed in the j direction. They're both moving toward the x-axis within this frame at the same speed, and they're initially at equal distances from the x-axis, which means that when one gets this far from the x-axis, the other will also be this far from the x-axis, so they will collide. And you can set that up as a system of equations and prove it algebraically, but that argument really suffices if you understand it. Okay, so anyhow, here's what things look like in the drone frame. Now let's proceed to a little bit of analysis. Let's make sure we've got these vectors right and so forth, and then let's make sure that momentum really is conserved and kinetic energy really is conserved.